Welcome back, Nature and Code. We're in chapter 4 and we're looking at mutation. We created this code here that essentially creates an original DNA sequence, makes a copy of that sequence to fill up a population, and then over time mutates bases in various sequences according to a mutation rate. So this seems to be working fine, and we've just established that you very quickly get quite a bit of genetic variation in your population because of mutation. Now, there are two things that I would like to do. One is sort of a housekeeping cleanup to make sure that things look good. And the other one is perhaps a more subtle fix, a slightly subtle error. It's not a computational error, it's more sort of an error in logic, but I will get to that in a second. So the first thing I'd like to do, if you look here at our output, this is not very clear. I just happen to know that this is the first, this is the population at generation 0, and these strings down here are the pop that are representing the DNA strings in the population after 100 generations. But I want to plot that information, or to show that information in the console as well. So what I'm going to do is quite simple. When I print these sequences, I want to pass a title along with it. And so in this particular case, I might just, say generation. So pass a string, generation 0. And down here, I might say, after 100 generations. Oh, oops, sorry, 100 generations, or something like that. And so print sequences now passes on a parameter. So I have to make sure that in my definition of the function, I can actually deal with this parameter. So take it in as an argument, which I'm going to call title, and then I'm simply going to just print that title into the console like this. And you know what? I'm just actually going to add another line break here, just like this. So if I save this now and I go back to the browser and I reload this, here's what I get. And this looks much nicer, right? So we see here generation 0, then here's the population, then a little bit of space, and it says here after 100 generations, and here's the population. So that just looks a little nicer. All right, there's a more subtle thing I want to say, and I want to fix, and that's down here in the run generations function. So remember what we did here. We went through each generation, and in each generation we went through each of the sequences, and for each sequence we went through each of the base pairs, and we said, well, is it now time to change the base given this probability, given this mutation rate? And if so, here's what we did. We just drew a random base out of 4 possible bases and assigned that to the corresponding position here in the array. However, this random base, which we developed in an earlier video, really doesn't care what is already there at the base. It just generates a new base. And so every time we do this here, there's a 1 out of 4 chance that we're actually not mutating the base. For example, you could already have an A here, and this function returns an A. And so it saves an A where there is already an A. So that is not really mutation. So I want to make sure that we truly get the mutations that we want, or truly mutate at the rate that would be the appropriate rate, and it's defined here by mutation rate. So again, there's multiple ways to solve this. I'm going to solve this now by basically adapting the function random base. And what I'm going to do is I am going to pass this value, whatever we currently have, I'm going to pass it as a parameter to this function. So up here in this function, I need to make sure I receive it, and I'm just going to call it current base. So the argument here is going to be called current base. And so now I'm going to do something that uses a construct that you haven't seen, which I will explain in a minute. So I'm going to say var new base, underscore base. So the new construct that I'm using here is the following: do, and then curly brackets, and then after the curly brackets, while, and these parentheses. So this is another form of iteration. The only iterator that we've encountered so far was the for loop. Now this is another type of iterator. What this says is do whatever will follow in here within the curly brackets, execute this code in here, which we'll have to define, while some condition will be true. So in many ways, this is the same thing as a for loop. There are two subtle differences. The first difference is that whatever is in here will be executed at least once, right? It will say do this, and then it will check the condition. So it will be executed at least once. That's not necessarily true for a for loop. You could set up a for loop so that this condition in the for loop, for example here, would be wrong or false, I should rather say, right from the get-go, and this code would never be executed. You cannot, however, create a do-while loop that doesn't execute at least once. And the other thing is do-while seems handy, but however, you don't have the benefit of having this I here. And this I, as you've now seen multiple times, or whatever you call this counter, is actually kind of a nice feature to have, because you can use it as a index when you iterate over an array. All right, so what is it that I want to do? Well, what I want to do is I want to say, give me a random index. So I'm going to put this up here. And then I'm going to say this new base that I defined up here but haven't yet initialized it is exactly here my basis, and then of course the index. And now I have to make sure that the bases are actually defined before I get to this line, because otherwise it would throw an error. And then I'm going to return new base. Yeah, so basically let's see what happens here. So we define a variable, we don't initialize it yet, no value. We have our basis here, and then we say, okay, do the following at least once. Well, generate this index, which is a random number, either 0, 1, 2, or 3, and then the new base is exactly the corresponding element here in the array. So now I can say, well, do this while new base equals current base. And now we solved the problem, right? Because now if this is true, after I've picked this random index and I picked a random base here out of these 4 values, if this here is true, if I actually happen to pick the same base that I passed here as a current base, then I'm just going to continue. And it's going to continue until it doesn't pick the same base. And so this solves the problem of picking a base that we already have. Now there's one other thing. When I generate the first sequence here, I also have to pass a parameter, and you could just pass anything here that isn't actually a real that isn't actually any of those 4 values. So I'm just going to pass in, excuse me, the empty string, because then I know this condition will never be true, and I will always get the first base that's being picked, which is of course fine in the beginning when I generate the first sequence. Now, one other thing I could do, and I should maybe do, is often when you have something like this that you might reuse later on, you could actually define it up here as a global variable. And then what you often see in other programming languages is if there's an array or any sort of data structure, be it a variable or some list or array that has values that should never change, people often use this capital letter notation. So I'm going to do this here as well, and so I just have to make sure that I'm using here basis.index in capital. Now, this doesn't change anything about the code. It's just, I think it's better style. JavaScript doesn't actually have a construct that allows you to really make this immutable. So you could later go somewhere in this code and you could start changing the values, and JavaScript wouldn't throw an error. So it doesn't have a construct to really enforce that. However, if you make this all capital, then it's really assigned to everyone else who might work with that code. Don't change that. This should be treated as immutable. And if we now save this and reload our browser over here, nothing should change. But actually, what we would expect, and indeed this seems to be happening here, we should see a little bit more genetic variation, because previously we had only really realized 75% of the actual mutations, because in 25% of the cases we didn't actually change the base. Now we're making sure we're changing the base in 100% of the cases when we call this function random base. All right, and that concludes this video. I'll see you in the next video.